Okay, so this is page 507, 8.4, example 4. We're going to use the error bounds to find the bound for the error, where t3 of x is the third Taylor polynomial for f of x equals ln of x at a equals 1. Check your results while using a calculator. And then I couldn't format what they had in the text, which was this error bound, which is right here. Okay, that's your error bound. See, bounds being the absolute value. So that is the value that we're looking at. And from this information, we can gather a few things. One, we can gather our n. Our n is equal to 3, because they've given us that. We're looking at the third Taylor, and they're looking for the error if using the third Taylor. We know our x, if you look right here, x, our x is 1.2. And we know our a is 1. Okay, we also know our f of x, which means we can go ahead and figure out the necessary components for the Taylor polynomial, which we're going to need, because this part right here, check your results while using a calculator. So check your results while using a calculator. That is where we're going to see this value, what we did in class, where we actually subtracted out to get the actual error. So they want us to do this to compare this part over here. We're going to get an error bound using the formula, and they want us to compare this to this actual error, just to see how similar they are, or if they follow suit. Okay, so I also need the k in this component, and the k, because I have the a, I have the x, I have the n, I have the t, n, and the f, I need the k. And the k comes from f n plus 1 of x is less than or equal to k. Now in this case, I know that the n is 3, so n plus 1, I can actually change that. It won't let me change, so I can change that n plus 1 to 4. So I need the fourth derivative here. So both for the Taylor, I'm going to need through the third, and for this error bound, I'm going to need the fourth. So that's the first thing I'm going to do. I'm going to pause it, and I encourage you to find the 4 derivatives for ln of x. Okay, so I have the first, second, third, and fourth derivatives written down now. You will notice that the fourth derivative, which is right here, is what I need to figure out this k, because that's what the f to the 4 of x, so the fourth derivative of x, the absolute value. Now, in the previous slide, I said that k is actually the maximum. So the max value of the fourth derivative is what we make our k as. So let's look at this f of x equals negative 6x to the negative 4, which is negative 6 over x to the fourth. Okay? Now recall that this x is really u, whereas u has to be between a and x. So a is 1 and x is 1.2. So I'm not looking where it's the max overall. I'm looking for where it's the max on the 1 to 1.2. And in this case, this function is decreasing, inverse proportional. So we have to consider 1 to 1.2, where we'll end up with our maximum value. Now, we're looking at the formula. It's actually the absolute value of that. So we're actually looking at the absolute value of negative 6 over x to the fourth is less than or equal to k, which is what we're essentially going to set k equal to. And 1.2 in the denominator here will actually make this smaller than if we just put 1, because that will give us 6. So at x equals 1, the absolute value ends up being 6. If we put 1.2, it'll end up being less than 6 once we assess the absolute value. So therefore, we're going to make our k equal to 6. And that is the max value of the absolute value of f4 of x on 1 to 1.2. Okay? So now we have all of our pieces. We've got the stuff that we need to make the Taylor polynomial. We've got the stuff that we need to make the Taylor polynomial. And we've got our k. We know x is 1.2. We know a is 1. We know n is 3. And we know k is 6. I think I said that. And so that's actually going to give us an error bound. So let's do the error bound first since we have everything we need. I'm going to highlight it all in blue. I have k is 6. I have n is 3. This is 1.2. A is 1. So, shrinking it down, and then I will do the work. Okay, so taking this formula out, we have 6 times 1.2 minus 1 to the 4th over 4 factorial. So that's going to be 6 over 4 times 3 is 12, times 2 is 24, times 0.2 to the 4th. And that is going to be approximately equal to, it's supposed to be a curly Q, 0.0004 according to the textbook. I'm going to check that. All right, so I checked it, and that actually matches. So 0.0004 is, what that represents is the error, according to that error bound, if I use a Taylor polynomial of an order of 3 with an x at 1.2, Taylor polynomial is centered around 1, then that is the error that I'm going to get for that, the Taylor polynomial t of 3 for that function. So now what we need to do is we actually need to create the Taylor polynomial, and we need to assess the Taylor polynomial at 1.2 and see what the actual error is. So using this information, go ahead and write the Taylor polynomial. So I have the Taylor polynomial written right here. That's the Taylor polynomial. So now we need to assess the actual error by plugging in the 1.2 into the Taylor polynomial. And then assessing the f at 1.2 and finding the error between. Okay, so written in I have t at t3 1.2, and that's that value. And then f of 1.2 is that value, making the difference between them 0.00035. Now notice there's a difference between these two. Recall that this is called an error bound, boundary bound. So we're not talking about exact error. The error will be at most 0.0004. And sure enough, this is less than 0.0004. So the error bound was correct and provided a boundary that you will have an error less than this, right? Your total error is less than this value, which is true. So this becomes 0.004, and when I actually calculated the error, indeed, I got 0.00035 is less than 0.004, which was this value.